like an hour and a half of my life trying to teach people how to use Excel. It was a good time. So if I seem short, it's because I'm annoyed. It's because I'm annoyed. I mean, they're not usually needy. I mean, they're not usually just so needy, so I was like, okay. Okay. First things first, let's get some information. So hopefully if you've done this, you've got access to this information. I'm just going to write individual things. I'm not going to write the whole thing. It says a fairground ride spins its occupants inside a flying saucer-shaped container. We talked about this yesterday. That particular ride is the one I was referencing in lecture. If the horizontal circular path the riders follow has an 8-meter radius, so R, had how many revolutions per minute? So this is essentially a version of W, right? Will the riders be subjected to a centripetal acceleration 1.5 times that due to gravity? So first thing I'm going to do is try to figure out what 1.5 times that of gravity is so that I'm using a number. I got 14.715. And that's going to be in meters per second squared. Okay? Yes?
What is FC? I know you
FC was that's the centripetal force from the other day. AC is centripetal acceleration. FC is centripetal force, but we weren't asked anything about that. Okay, it says how many revolutions per minute. So that sounds like we probably need a W. Okay, and so yes, so I went through before we started class and I put all of the formulas we've discussed so far in this chapter on the board, using one of those centripetal acceleration formulas. I'm specifically going to use the one that we derived that has W in it already. And I'm going to try to calculate what W is with this particular equation, okay? Because it says I eventually want to get into revolutions per minute, which is a form of W, not necessarily W itself, because W is in radians per second, but we can always convert radians per second into revolutions per minute once we have a value. Do you agree? Mm-hmm. Okay, so let's solve for W. AC was going to be this. Do you agree? Mm-hmm. Okay. R was given in meters, so I don't have to convert it. And W squared. Okay. And then I do square root. And I got W equals 1.356. Yeah, I got 1.356. And remember that W will always be given when you're doing everything in the units you're supposed to be doing them in radians per second. So the next step, revolutions per minute. Remember to put your 2 pi in parentheses.
4.95.
That's what I got. Is that an answer? Is that like a free response? Oh yeah, it is enter your response. Cool.
Type in first and then it's a 12.9.
So you said 12.95?
Yeah, but 12.9 is like, it makes it better. I'll type in the answer and then my answer is actually
I'm like doing your homework right now. 12.9 is an answer.
I hadn't gotten to 12 yet.
Okay.
But that makes
Cool.
sense, though.
What's
Like,
next?
I just have a question. Yes. So it says for the formula.
Jess, what number is that?
That's if we want to calculate the change in, if we want to calculate W using radians per second. That's like the, you remember how like v is distance over time? That's like the same
I
thing.
don't the change in my
Yeah. So this is the.
You're blocking my entire rejects.
You're gonna make me cry up here in front of the entire class.
Does that help? So do you remember how like we don't really talk about it, but v has a unit in meters per second. We initially, like way back when, introduced this as delta x over delta t. Do you remember? So that's like the general form of w. We're gonna use the assumption that we understand that it's radians per second to do all of the rest. Okay.
Okay.
What's the next one?
Do you guys want to talk about the clock one? Have you guys seen that one? The 3?
And then I already got it wrong.
I also was super confused about the fan
fan?
spin one with the
Whatever that.
Angular displacement before it stops is the question. So angular displacement would be delta s. That was question 6 that she's talking about.
Delta
So it'd be that first equation on the board?
Yeah.
Okay.
So
It would be angular. So delta s is arc length.
So that'd be 5 over. What's the radius of it though?
In degrees is delta s.
Oh.
So change in degrees over time, or over r.
I was confused by the square root on those.
Well, am I doing 6 or am I doing a clock one?
Yeah, I don't.
Yeah.
You want to do the fan?
Yeah.
Okay.
There's not much information given. So.
Okay. Can I erase? Okay.
Thank you for doing this problem.
Anytime.
The conversions remind me of Ms. Messenberg's class.
I'd rather spend time going over homework problems and helping you understand where you need to be than whatever. You're gonna do an activity either today or tomorrow. Tomorrow is just as good as today. Okay, so, what?
Actually, that's like a good quote.
Our fan spins at 6 revolutions per second. If this is what you need, then this is what we'll do. When you turn it off, it slows at 1.0 revolutions per second squared. What is this from? Okay, just give me 1 second. Does that matter? What is the angular displacement before it stops? Okay. I wouldn't say that, but I appreciate that. Okay, so if we had to talk about angular acceleration, I want you to remember acceleration in general. What was the formula for general acceleration? Does anybody remember? A was change in v over t, right? So what would it be if we wanted to use w instead? Ooh, ah,
Is it
ooh, ah.
Is it AC equals?
So how do we convert v to w?
V equals W.
R times
Over
W?
v equals rw, right?
Mhm.
So let's do a w final. Over t. I'm going down this rabbit hole on purpose because technically we didn't talk about angular acceleration yet, so it's interesting that they gave you this problem in section 1. So here's where we are so far. And this is angular acceleration. to tell you what the, it's alpha. We're not there yet, but it's alpha.
That's one of the questions. And I was like,
Why did it give you those questions in section 1?
Because OpenStax is mean.
OpenStax is mean. Okay. All right. Okay, but that's okay. Well, let's try to get through it. Let's try to get through it. Okay. Let's calm down. This is our initial speed, right? So this is W initial. What is W final going to be if the fan is coming to a stop? 0. So this is going to be 0. Okay, we were told that the angular acceleration is this. Zero minus 6 revolutions per second over t. Okay. So here we are so far. This is interesting. I mean, t has to be 6 seconds. But I digress. Shouldn't this also be negative if it's coming to a stop? Do we agree with that? Okay. All right. We're doing good. We're doing good. Yes?
So why did W final R become 0?
Because it's coming to a stop. It says in the problem that
So it doesn't matter that
it slows to a stop. So since W, it doesn't matter. What do you mean? Sorry.
it doesn't matter that there's no R.
No, it doesn't. Nope, because we were given what W is. So it doesn't matter that there's no R in this. I mean, we could say, oh yeah, there's R, but this is 0. It doesn't matter, is my answer to you. Because we don't care too much about how far away the spin is happening. We just care about how long it's going to take. Okay, so our whole goal behind doing this particular exercise is to figure out what T is. Yeah.
Why is that second squared and that just regular seconds? On the bottom, like the
Acceleration.
Oh.
It's an acceleration, yeah, sorry.
Yeah.
Yeah.
I was
Okay.
thinking-
So,
Okay.
hold on. So now we have that this, negative 1 over 1 equals negative 6 over t. And I want t. Yeah, so what should t be?
It's so cute.
6 seconds.
Okay, so there's the first thing we could get. But we want the angular displacement before it stops. So how many times is it going to go around before it stops is our question.
6 reps per second in 6 seconds.
So mad. Okay, so, okay, so, damn it.
Me too.
Here's the problem. No, here's the problem, is they gave you a problem that requires the kinematics formulas. And you can't do it without the kinematics. Because at this point, you know time, you know initial, you know acceleration. If you aren't tracking this so far, we're at here. No, I mean, you can type in whatever you like and get it wrong, and I won't penalize you in your homework for this one. But you have this, you have this, you have this. You know V initial, you know V final. Like, do you see, like, if we were doing a kinematics problems and we had these 4 things, you could solve for the thing you're missing. But you can't solve for the thing you're missing because we haven't talked about kinematics in the angular direction yet, and I don't know why this is part of your homework. I apologize. The system decides the questions. Like, I only decide half the questions. The system pulls the rest based on your answers to those questions. And I don't know why it would have given you a kinematics formula before we even talked about kinematics formulas. I only selected sections 1, 2, and 3, which don't include the kinematics formulas. So, throw 6 out. You can yell at it. Is there another one that has an angular acceleration in it? Which one is your one for the clock?
What's the clock?
That's number 3.
Yeah.
That should be okay.
Yeah.
It doesn't tell you if you got it wrong.
That's because I didn't press on it because I wrote my thing and I based on the answers.
I mean,
worked through it.
okay.
I don't want to just.
So now let's draw a clock.
I've gotten 1 right. I don't.
9 o'clock is over here.
That's a 20%.
This is 9.
Yeah.
This is 12. This is 3.
I feel so much better.
Hold on. This is 6. It says the hour hand is half the length of the minute hand. Oh. This is the minute. This is the hour. I like it. This is one of my favorites. You have to think about it. So you have to think about it, first off. And it says compare the distance traveled by the tip of the minute hand to the distance traveled by the tip of the hour hand since noon. It's 9 p.m. How many times has the hour hand gone around the clock?
9 times.
No, the hour hand, guys.
Oh, wait, what?
Since noon, the hour hand has gone this far. The minute hand has gone around the clock 9 times, guys.
We know how clocks work.
Yeah, clearly we know how these clocks work.
That's only 6.
The minute hand goes all the way around every hour. The hour hand only goes around every 12 hours. So the hour hand is only gone. So let's talk about angles, right? Let's talk about how far one has gone versus the other. This one has gone around 270 degrees worth, correct? This one has gone around this many times. God, this is hilarious. Clearly we don't spend a lot of time looking at an analog clock, and in my classroom isn't going to be helpful because we don't look at a clock in my classroom. So this is going to be how many revolutions this one's done. This one's only done 3/4 of a revolution. This one has done 9 revolutions. And you were supposed to talk about the distance one of them has traveled versus the distance the other has traveled. So could you theoretically bring in the radius to this equation?
Yeah.
Sure, you could. You could calculate this number. Delta S is the number of is the total angle, and R is the radius. So one of them is going to travel a lot less because it has a smaller radius, and the other is going to travel a lot further. One because it goes around 9 times, and the other because it has a longer hand. Okay? So really it's just like conceptual. It's not really give me a number. It's talking about conceptualizing. And if we aren't sure how a clock works, then it's probably pretty hard to conceptualize. Very concerned. Okay. Okay, so it does say the answers in A through D are how much further does the minute hand move compared to the hours hand?
A lot more.
So you would divide, I would say get the total angle and divide it by 270. So 360 times 9 is what?
3,240.
Divided by 270 is 12. That's not the answer.
That is not the answer.
And I thought it was.
Well, but then remember, the minute hand is double the length, right?
So you double it, so it's 24.
So the minute hand is double the length, right? Because the hour hand, it says the hour hand is half.
The answer is 1440. 1,440 times. I put 24, and that was incorrect.
That of the hour hand. So this one only moves. Yeah.
So isn't the minute hand that goes around like 6 times per hour, so it's going around by the time it gets to 90 pounds?
The minute hand goes around once per hour, right?
The hour hand, doesn't the minute hand go around, so it'll go around?
So it'll go around 9 times, right?
No, it could go around 60 times per one.
No, that's the seconds.
Oh, wait.
Girl.
The minute hand goes around.
You know, we're thinking about
Wow.
No, yeah, wait.
Clock. The clock
hate
is
clock.
hard. I did not
I
know the
have a
clock was going to be this
smartphone.
hard. I'm sorry.
It goes around 60 minutes. Yeah.
Wait, what's the question?
But like if it's by the time it's gotten to 9 o'clock, it's gone around.
What's this? I want to do
It
this.
doesn't go.
I still think it's supposed to be 24. I don't think it's
per
supposed to be
hour, so it's
1440.
around 630.
So the system is flawed once again.
Hold on.
Is it around 60 times?
Times 9
Yeah, it does. Yeah.
divided by the radius. So let's just say this is R and this is 270 divided by half R.
Because I got an email. We met our goal. I don't know what the goal was. I don't know. I'm pretty sure it's money related. But we get Tuesday tomorrow too.
Wait, when you go from when you go from an angle to radians, is it 270 times?
No, I don't know. That just makes so much. Oh my
Does it
God. We need a visual.
Yeah, I'm putting it into radians to see what happens, because I feel like we're supposed to be doing it in radians. So this is for the hour hand. That gets us in radians.
Oh my gosh.
What'd you say? Yeah. This one did not convert. It was like, I love that you're trying to use me this way. That number divided by 4.71.
Honestly, personally, this makes me feel better.
What'd you say?
What? Yeah.
That's how many times it goes around for 9 hours. Oh, I converted to radians. But I should have divided by 360. So that should be 18 pi. Is that what you got? I still got 12. It still came out to be 12. I still think the answer is supposed to be A and not D, but does it give you any information about 1440 times further than that of the hour hand?
I think it's like
It doesn't though.
I think if it's like when you're wrong, it's not.
What did it say?
I don't know. I tell you like a
It
drop
usually
that box.
doesn't say anything public.
Like
I'll just say like.
Well, you got that one right.
I'll be like, please review. It's like, review what?
Yeah, some of them will give you an actual information, but okay, well.
Oh, are you gonna?
I'm sorry that the clock problem is wrong.
Is it for the one that's due
I can
tomorrow?
write an email. What?
It's for the one that's due tomorrow.
Well, so remember, you guys, this is the first year they're using this system.
Oh,
Oh.
really?
Yeah,
It's really
it's a
good for
beta.
it
I mean, it says beta on it when you do it. So there are questions that are wrong. We've come across them.
I like to get it wrong though.
So I will send an email and let them know that that one's wrong.
Do you want to see what it says?
I still think it's supposed to be 24 because it's 1/2 the radius, and you're comparing how long they go around. So I still think it's supposed to be 24.
Should we see what they say?
You can try. Sure.
Well, okay. It's not gonna count towards my grade.
Oh, is that one of those?
Yes, I saw it sitting there and I was like,
I know, I saw it yesterday. I was like, I want to grab it.
it's an avocado.
It's a something.
So I just got it wrong.
You got it wrong for no reason. Well, you were a test pit. You were a test
There's
pit.
stuff I need to snap this. This is the cutest thing ever.
What?
Your avocado.
Oh, my wobblecado.
Yeah.
It wobbles.
Oh, a avocado. I'm gonna say that.
Cool. I still think it's supposed to be 24 because the hour hand is half the length of the minute hand, and if you compare them directly, you're at 12, but since one is half the length, it should go up to 24. Okay, are we doing any more of these? Have we gotten to the acceleration problems, the centripetal acceleration problems yet, towards the end?
No.
No?
I didn't even get near the end.
So, what is the clock problem, I would still, if I were you, I would say A, and just get it wrong. And then for number 5, nope, the 6. No, number 5 is the fan spinning at 8,362 degrees per second. How many times did it spin in 5 minutes? Oh, you got that one right. Good job.
Thank you.
Number 6 is the one that we were talking about, revolutions per second. I'm going to get it wrong for you. You're welcome. Are there any other ones that we need to? You haven't locked this one in. I'm going to lock it in for you. You got it right!
Yeah, you're right. Wait, which one?
Number 7.
Oh,
You wrote it in, like you wrote in your answer, but you didn't hit the multiple choice part.
because it wasn't close. It was off by like decimals.
What are you talking about?
But then that's
What?
right.
2.15 versus 2.2?
Oh, I don't know why I didn't look at it.
Okay, how are we feeling about centripetal acceleration today? If you get to an AC problem, you should be able to get through it. But I think part of the problem is we need to practice our manipulating the different equations, right? So this is the first time we've seen them all in one place from the start to the finish.
No matter how you drop
What would you like to work on today? Would you like to work on your activity or would you like to work on your homework?
Homework.
On your homework is the activity.
Wait, what's the activity though? I would like to know what it is.
No, not yet. We're not there yet. But our activity is tracking how mass and speed are related for objects that roll down ramps.
Yep, that's a Friday. That's a Friday.
Only the Friday thing?
Yes.
Are we gonna mix them?
Yes, ma'am.
Number 2
'Cause this is due
has
tomorrow,
the
so.
infinity.
Look, no matter how I drop it, it lands like that.
Alpha?
The
Oh my god. Because it's a wobble-cado.
Aww.
Wait,
So alpha is average angular
it's a
acceleration.
to land. Look at it landing.
Oh, okay.
It's like hard at
that
the
would
bottom.
mean that it would.
So treat it like an acceleration. So how would you calculate the time?
Yep.
It says, right?
Yeah.
No, it says which equation is the acceleration after switching it and you measure the time. So you have T and W.
I know.
So how would you measure alpha?
Oh.
I'm just like obsessed with this. I want this.
Well, this is Here's the other one though.
I didn't.
Here's these ones, like the, because this takes into account initial and final. Oh, fine, keep going. You should still be able, hey, listen, I just looked at this problem number 2, and it does have, so I want you to answer what you think you can do, but it does have alpha. Alpha is angular acceleration, so treat it like a kinematics problem in number 2. And I guess we'll just preview what we're gonna do next week. I'll write them up here for you. That's really annoying. Cool.
Oh my goodness.
What's wrong?
Stress.
I know.
I don't know what it is. I'll figure it out.
Find the ones you do think you can do well on and start with those. Because there are some that are pretty straightforward. It's like centripetal acceleration, what is time, that kind of thing.
Who even knows?
Lilia.
Oh my gosh. The kinematics equations are in chapter 10.
Not really.
Are you kidding me? What?
See, I know what I'm talking about.
Do you now?
Yeah, I know. Hi, y'all. We digress.
These are the analogs. The rotational quantity is on the left. The linear quantity is on the right. So in other words, you can replace the things on the right with the things on the left. You see that? Okay. These are called the rotational analogs. The ones on the left in that box can replace the things on the right. In the kinematics formulas and any of the formulas
That
we've
deserves
seen.
a picture.
That is not a direct relation. There is something you have to do to actually directly replace, but when you see them in the kinematics formulas, so for instance this one, this is one of our kinematics formulas. All we have to do is replace the different variables. That's a hint, but seriously, we don't get to that until chapter 10. We cover gravitation. I know. That's why I'm very confused as to why they're asking you about kinematics and the rotational, because we didn't even cover that in the I'm gonna go back to problems in the book.
Yeah, OpenStax has caused me so much pain, Michelle.
Okay, I'll stop doing homework in OpenStax, and we'll start doing we'll keep doing reading in OpenStax. You're still gonna have to do your reading in OpenStax, but I'll do homework sets like.
Yeah, me too.
That's, I mean, hey, listen, again, it's the first time I'm using the system, and the system is clearly slow.
They're not very good.
I mean, they're not bad.
Like, this is
For the first year launching
my
this
God.
new system.
Well, the thing is, the
They only
system
launched
works
the first two books.
Yeah, the system works fine, and they got it all down. It's just
Well, and I think the
The
problem
problems
is
are
that
also worded really weird. Like
they aren't correlated. That's the problem. Like in number 2, it's asking you about a kinematics formula. We're in chapter 6. That
last
doesn't
two.
appear till chapter 10 in this book, so it doesn't make sense that they've done.
yeah, that's
It says, which of the following is not an expression for angular speed? I said, I don't know because there are no options. Yeah, yeah.
For which one did you put that down?
Number 1. Oh.
I will not count this against you.
Yeah.
I'll
R times
just count it
W.
as done. So
It's
just
R
finish
times
it up
W.
today. Get it done. We are going to do other problems with these equations next week. I'm gonna reapproach this. I'm sorry.
One time I did a problem and it was like what degree or what angle
I'm so
was like
literally
what
like,
degree.
what?
And it said it asked me and it said like that sounds kind of easy and
Yeah.
it was one of the answers. Same way I
Hey,
did it.
Jess.
But they said that that's not what they were looking for. So I was like, I could have gotten it wrong if I just like changed it. But I was like,
Yeah.
Your eyes look so
See,
like
and that's what I'm saying.
glassy.
Like, I think it's just new.
I don't know.
It's new. It's flawed. It will change.
I don't think it would have to do something through it. I just get confused really easily.
Yeah.
Did you do Numero Uno? I'm doing it right
Again, all
now.
I can do is change
I've eliminated 2
If it works
options,
for reading,
but now I'm confused.
if it
Hey,
doesn't
Jess.
work for
I
homework,
eliminated 2 options, so
the homework
it's
system
not A
needs
or
to
B.
be improved.
I feel like
Is
it's
my
D.
feedback.
Oh,
Oh, you
My
have to enter a
camera's
response
on.
and then you have to.
I don't know. It always does this.
It was a filter that said wake up and be
Wait, look at
awesome.
Okay. I really think it's D. I think it's D.
It's not
Okay. Numero Uno is J.
What's not angular speed?
Force.
Is the
No, because there's no options.
radius?
Because there are no options.
Yes.
Oh, I need a stress avocado.
Experience with the center of a round track that is 0.1 meters across. Oh, no.
You can
So
just
that's
do it
0.1
at
meters
Ericsson.
across, so that's the diameter is divided by
You're
two.
really killing me.
Okay. And it completes 1 lap in 1.3 seconds, and you have that C equals how many C, right?
Thank you.
So yeah.
So you need A.
W?
I need A,
Angular.
which
You can get from V squared over R.
No.
So if you know how
No.
long it takes for it to go around, it does 1 revolution in 1.3 seconds, right? So it would be 1 revolution per 1.3 seconds will be your angular speed. And then convert that to radians.
Oh my god.
Grab homework.
Okay, which equation would you use to calculate the average angular acceleration of the edge of a record
So it means a 90-degree turn in 0.5 seconds. Okay? And yes, it's in C. Okay. So this is
A
sorry.
sub C
Yeah, yeah.
equals.
Okay, so give me 1 second, okay? 1 revolution, 1.3 seconds. Is your W. You do need to convert to radians. Okay. Once you have W, you can do.
It's like this had to be a baddie.
this is not a few baddie.
She goes,
I have to start thinking about like this.
Multiple approaches, lots of different things you have to do.
Dude, my camera's on.
have no.
Wait, do you have a signal?
Why'd you put
Oh no, I think I have a stalker.
Do that.
Wait, that's so creepy. I just watched your physics right now.
Okay, so
Here, do this. Tape.
what are we doing?
Does she have tape over here?
Make it
Make it blurry.
Is that gonna work?
Maybe. Color it
Wait,
black.
wait,
And that's
I have
1/4 from horizontal. So remember, horizontal to vertical or
Dude,
doesn't matter, it goes either way.
I literally
gonna
feel like
do-
the government is.
Yeah, that's what I said.
Radians?
Color it black.
That's what I'm saying.
No.
Wait, is there a
Oh my God,
Sharpie?
it's not working.
Here. Use a purple
Yeah.
Sharpie.
Two heads, 1 revolution, right?
That's
So
not the
then
first
0.5
time.
pi should
Really?
be 1/2 of 1/4.
That's so big.
I think it's because I'm going on Eagle.
Yeah, I go down there too.
When acceleration is
No,
felt
I have like all these notifications. Look about.
is felt at the tip of her racket if it is 1.3 meters from her shoulder. So a radius, right,
Wait,
is 1.3.
It's like I have viruses.
Okay. Okay, so we want to know acceleration. VC of there
Sorry, what?
can equal R.
Yeah, it is. That's the right one.
Is this a W?
Why is it three holes?
So convert this, so this is already in radians, if you just multiply this out. Okay?
I'm getting
Alright.
angry.
If you have questions
not gonna
on your
work.
homework set, please
Hey.
do ask. It doesn't mean you don't have to do it, and you can do most of the ones towards the end of the set. want you to practice using the formulas. And remember we talked about yesterday in depth about having a multi-step approach. So you may have to do 2 or 3 things to get to your final goals, right? You may have to calculate a W in radians per second before you can calculate A equals RW squared.